everyone and welcome to Cioriia podcast. For this episode we are talking about computational physics. I'm here with Stefano and Lorenzo.
Hi.
Thank you very much for coming. Lorenzo has done a PhD in nuclear engineering physics. He's been on the podcast before. Thank you so much for joining again.
You're welcome. You're welcome.
Thank you so much.
I'm happy to hear.
And to participate.
It's a fixed guest.
Exactly. And Stefano, he's the first time on the podcast. Stefano has done a PhD in biophysics, and more specifically, maybe you can give some background into what you have done before.
Yeah, I did.
What you are doing now.
Did a PhD. Actually, it was statistical physics at the end, but it's true that it was applied to biology in the general sense. In particular, applied to avalanches of fractures in living cells. So I was modeling these fractures, and we were comparing cancer cells and healthy cells. So
Okay, and
from
that
the point of view of these avalanches that were induced by AFM experiments. I don't know if you know what is
maybe
AFM.
no.
It's atomic force microscopy, which is basically a microscopic needle that goes inside the cells, and you measure the response of the cell, the mechanical response.
Mechanical. Okay, so you just punch it basically. You don't electrocute
The
it.
cell stays alive all the time along the experiment, and you measure it, so you can induce this breaking in the cytoskeleton of the cells. I was modeling this.
So you're basically a cell killer.
Yeah, but
kind of.
but the cell was staying alive. So.
Okay. So you didn't kill any cells.
Sometimes some cancer cells.
We need to think about the ethics of cells right now. The cells have a soul. Do they have consciousness? I don't know. Maybe for another podcast.
Intriguing question. What is life?
What is life? Yes, of course. And Lorenzo, can you tell us again a little bit about your background?
Yes.
Just a short summary.
Yes, I am an engineer. I have done the PhD on nuclear reactor physics, and having a thesis related to the calculation of cross-section in the field of light scattering, like in photoelectric effect. And now I am outside the academic career, and I'm working for a private company as an engineer.
Great. And now, just to give a bit of insight into the motivation for this podcast. So the idea for this podcast is to discuss about computational physics, and the reason why is you can confirm very well, Lorenzo. We talked about this before. The computational skills that you got during your PhD is what saved you. What guaranteed you a job in the end, isn't it?
Yes, because I was quite skilled in programming using C language, also Fortran language, even if Fortran is not very common in the industry. And so these skills helped me a lot finding a work. No once every time I present my curriculum to someone and looks at my curriculum and says, what are nice topics, but what I can give to you, where I can put you inside my industry. I don't have nuclear spectroscopy. I don't have nuclear light scattering. And no one starts thinking about, okay, maybe this guy has done a lot of good things and also has done a lot of complicated things. Maybe he can use his brain for helping us to solve all problems, which is because, in industry has its problems, but they are not nuclear reactor problems. So I can say to you that they are complicated but not complex, and they can be solved in a linear way. So you taking your Fourier transformation or all the harmonic of your problem and then analyzing all the harmonic and getting a solution, and it's just a matter of time. And sometimes I find that the industry world is a little bit blind on the effective capability.
It's strict.
Yes, effective capability of nice people coming from for example, physic degree.
So you'd say that companies don't really know how to use a physicist.
Sometimes
more or less.
I have this feeling.
Yeah, the most common thing is that they put physicists to do software engineering.
Yeah. It's what happened to me.
Yeah,
Exactly.
You know very well.
So yes, so I think this is I mean
it still is good. I mean,
you know, but I think, you know, the main takeaway from this is that most people that join physics is actually because they're interested in you know, immutable laws of the universe and you know, things that you know are not created by people, right? We learn about you know, the nature of things, and you know, we want to learn deeply about fundamental laws and so on and so forth. But then again, there is a statistic that I've been referencing a lot on this podcast before in the previous episodes. Only 3% of all the PhDs actually end up with permanent positions in academia. So at least this is a statistic for UK. So we are talking about PhDs, not even master students. So
so already there has been first.
Yes. So almost everyone from that does a master's in physics. So after 5 years of higher education in physics, they have to find a job, and you know, most of them, I mean, maybe all of them, just get a job. 90%, let's say, you know, high percentage get a job just because they can do some computing stuff.
Yeah.
Otherwise, employers won't really look at QFT or general relativity or statistical mechanics or.
Yeah, I think this thing is very common in our part of the world, but maybe also in Italy is more common than in the other part of the world. Maybe I have seen this blindness on lots of different companies here, not only in Italy, also in Europe. It's a pity.
Yes, I don't know how it can be avoided, but I think at least for the people that enroll onto a physics degree, they need to be aware that, you know, they come up with these ideas, but at the end, it's the most time that they put into the degree, it's not actually useful. Like realistically, it's not useful.
There is also putting my attention on the companies, several companies' side. I understood this kind of rationale beyond this choice of not selecting, for example, people coming from physics, then engineers, and the reason is that, okay, you are coming to us because you are not able to find a work in what are you searching for, and if I take you, then after some months that you can find another job closer to your fields, and you will leave me, and I will lose a lot of money because I tried to give to you an education regarding the problems I have inside my company and so on. And so if probably you are using this work just for surviving, and then when you will find another one more closer to your topics, you will lose me. But the problem is that today is so easy to find a work that this topic is applicable to everyone. So all people can find a position inside a company, and then continuously searching for another position just for a matter of money. So maybe this rationale was more consistent with what is effectively reality in the past, but today is completely not applicable because everyone is continuously changing work, searching for more money. So in my opinion, there is no reason for not taking people coming, for example, physics academic career. Maybe it could be also better than engineers, who knows, especially in the mechanical field, electronic field, information technologies, chemistry, biological world.
Yeah, of course. Yeah, it's.
This is just my opinion for sure.
No, I think it's unavoidable at least. So let's give us a bit of time to discuss about what is computational physics. First of all, to let the audience know what we're up against. I mean, what we are talking about really, because if we think about computational physics, if I give you, for example, a question, name some computational physicists, you wouldn't be able to name them, right? So it's kind of a thing that you do.
There are some like famous algorithms that can sound familiar.
Yes.
For me, because
Yeah.
I can cite Gillespie because I'm using.
But
yeah, it's
they're
true
not.
that there hasn't been Nobel prizes for.
Yeah, that's right. Even though it's kind of Nobel Prize, it's usually the thing that you win because you made the most impact onto society.
Yeah.
And I think truthfully, just developing a good algorithm that gets used in all the scientific community, and also even more than the scientific community, because algorithms for optimization and so on are used in the industry and so on.
Every day.
Yeah. So I mean, if somebody comes with an algorithm like that, I mean, maybe they should be considered or at least nominated or something. But
I think that all these maybe first we are going to define.
Yeah. So can I get the help of you guys to define a bit computational physics and to give some background into what it is, because it seems like we cannot name people that are doing this so easily. So what it is? What is the bread and butter of computational physics?
I start. Well,
yeah.
I mean, I would say that it's all the physics that needs to use computations. So nowadays,
Right.
all the fields of physics are in part, at least partially, computational physics.
Yeah, except for maybe theory.
Maybe
If we-
except
like
like
string
group
theory,
theory,
maybe,
string
group
theory.
theory,
In this
something like
case,
that,
you don't need, but maybe you need to use also some mathematical software to solve.
Yeah, possibly. Yeah.
Solve.
So it's everywhere. It's definitely everywhere right now.
I think it's everywhere. Then, as I was saying before, probably the problem also because it's not considered as a pure physics. Is because until the 80s it was considered as a part, like it was more informatics, software engineering and so on. Then in the 80s it became popular, all the field of complex systems, and now is increasing its popularity every year, I would say. Like the Nobel Prize of this year, also Giorgio Parisi was coming from the field of complex systems. And in the field of complex system, all these things that were in between two domains, like in between informatics, physics, maths, they were included all together. So now it's considered also like, for example, neural networks that maybe before was something that only you were studying only if you were an informatician. Now it's part also of complex system because you can see it from a physical point of view. You can see from a physical modeling of modeling your brain at the end, and it became also an important part of physics. But
So
it's recent because the first center of a complex system was born in the US. Don't remember exactly where now, but in the 80s. So it's something relatively new with respect to other fields of physics.
I mean, in terms of computational physics, we have a bit of a longer history. Like it started with Bernie Adler in the 19 Adler or Alder. I have to check actually. Yes, the correct pronunciation. Yes, in the 1950s, and he was studying systems of hard spheres and seeing if a transition actually happens. It's just basically spheres that bounce off of each other, like perfectly hard spheres.
Are spheres in a bottle, like in a container?
the system was a 2D system, and he put like 100 spheres, and it was maybe bounded. Yeah. And then he would, I think, raise the temperature or something, and he would want to see if there is a transition from a solid to a liquid. And of course, at the beginning, it's incredibly hard with computers that were available back then.
First, it was not very.
Yes. It actually started also during the war, because they during the Second World War in America, because they received funding to study questions about nuclear decay and so on. So part of the interest was there to simulate like atoms and how they interact with each other. And slowly, because computers were available back then in the 1940s, although on to a different scale than today. So it started actually in the 1940s and slowly picked up. Transistor, showed up on the scene. And then more and more people got involved, more and more people had access to computers, and in the 1980s there were already a lot of computer centers around Europe.
And maybe to let people understand what is computational physics, you can think of someone who makes simulations, basically. You make simulation of what can happen in reality.
Mm-hmm. Would you say that
physics,
it's a one-to-one?
In a physical system.
Would you say that it's a one-to-one match between simulation and computational physics? Or
I think that nowadays what a computational physicist does, it's basically to do computations to simulate a real system that cannot be solved analytically or another way.
Sure. Lorenzo, do you have any ideas on the topic?
When Stefano was talking, I was quite fascinated by his shirt, because I think there is written something which is extremely compliant and consistent with our topic. I will translate in English what is written in Stefano's shirt.
Tell us.
From diamonds.
It's a song.
From diamonds, nothing born, nothing grows. From shit, flowers grows.
Alright.
It's not exactly shit. Okay.
I want to say this because you talked about a lot of nice things, and in this topic we are talking about Nobel Prizes and theoreticians. They are like diamonds, and this is true. I don't want to say that from diamonds nothing grows, because at the end we will use their solution quite fast in our development. But the shit is computational physics, because but from computational physics grows the flowers, really the flowers. And I will try to explain my vision of this, because you say that the one who is doing computational physics is just someone that do simulation. So you can figure out the computational physics like something like a little robot, quite isolated and yes, and a little bit how can I say alienated. That is 10 hours every day doing this little mesh of the world, trying to simulate everything using mesh. So finite elements methods, finite differences, and lots of different methods for using. This is not completely true, because it's a nice and characteristic vision of a computational physicist or engineer. I think that computational physics is a very, very powerful instrument. First of all, for trying to understand better what reality effectively is. So, going in detail and reproduce phenomena that maybe our system of measurement cannot catch, cannot make you to see very well something that maybe a simulation can explain to you better, and make you to understand better what is the effective dynamic of a phenomenon. But from the other part, can give to you an extremely important important feedback on what the theory effectively is saying, and also if the theory is effectively correct, because you can see a lot of things
but also
going
the computation can be incorrect, so
for sure, because and
you don't
here
know what to believe.
for sure, this is why here I'm saying to you is not a simply robot, because you have a poor guy that has got from one side the errors of a theory, because no theory is perfect. Has got his assumption and his theory and his errors. From the other side has got the computational errors, and these two errors can propagate inside in your computation, and you have to take care of these errors for understanding what you are effectively doing. So there is a parallelism between what is the computation and what is the physics of your system, and a good computational physics has to take this parallelism and try to, in a certain way, reproduce this dynamic of the system in the dynamic of the computation. It's not easy maybe to get, but sometimes is a crucial aspect of this. And this makes that sometimes who is trying to simulate something understand better what the reality effectively is, but also theory sometimes. I say this for my personal experience. It's just my personal experience and my point of view. But I have the feeling that if you are not a smart guy which can deal with uncertainty with a rational, systematic way, and also using a little bit of artistic solution, you cannot be a good computational physicist.
Artistic solution, what do you mean by that?
It's not, in sometimes... sorry? Creativity, because, you have
to find a way to make the code work, or creativity work.
Sometimes you have to do a little bit of improvisation, like someone which is playing an instrument. You cannot find everything in literature, and you have a problem, you know that there is a solution, and you have to find it, and you start thinking about it, and maybe one day you look outside the window and you say, oh, this is Bremsstrahlung, not Bremsstrahlung, sorry, the Rayleigh scattering on the atmosphere, and maybe you will say, remember, but Rayleigh scattering is something that maybe I can use inside the diffusion of a particle in a matrix of living cancer, I don't know, and you can have this, because the artistic solution is this way.
So we can say that it's important not to fix,
to
look at the screen,
to
look outside.
To have the
to
most...
be a computational physicist, you don't have to look at the screen.
In every topic, for sure, in every topic you have to have a broad view of what we are doing. But it's like what people do when they produce music, high quality music. I can say to you, Mozart Requiem, for example, which is one of my best rock and roll hits of the 18th century, and it was a really metal requiem, and it's a very, very nice collage of Bach, of Haydn, of Italian tradition. It's a very big collage, and he created something which worked perfectly. So I'm saying to you that when you have to do a work, you have to take your view very broad and use all the things you have for finding a solution that sometimes is outside the book.
Okay. So when we are talking about these complex systems and the errors of a theory and so on, are we also thinking that you were mentioning the example of the Rayleigh scattering. Maybe you can use that in cancer cells or something. It's a outrageous example, anyways.
It's brainstorming.
Yes.
Brainstorming, yes.
Yeah. But are we saying that sometimes, let's say you have a very simple example, you have many objects that are interacting via Leonard potential or something like that. Leonard Johnson potential, and then you let them interact, and you see something that's not actually encapsulated in that equation. But are we talking?
That's the heart of complex systems, I would say.
So it's like emerging behavior.
Emergency, yeah.
And
property of emergence.
How have you experienced this phenomenon in your work, emergence? So far. Maybe or actually maybe we can answer that question a little bit later, because I'm also interested. But first, let's give some examples of what are the tools of computational physics, because we've been talking that computational physics, exactly, can be anything. You can use it in any sort of field. You just need to be in front of the computer and put some equation, calculate it,
in front of the computer, but look outside.
Yeah, never get fixed on the problem at hand. But I mean, you are in front of the computer, so most of the time that you spend doing computational physics, of course, it's in front of the keyboard, right? Also looking outside, but I think you're just a physicist when you look outside. But when you're in front of the computer, then you are a computational physicist. So what do you actually do? Like, what do people do in front of the computer? Do they use the same tools? Are all people that are involved with solving physics with computers using the same tools? Do they read the same textbooks? Do they go to the same sources? What do we deal with? I know, for example, I can give like Monte Carlo. Everybody talks about Monte Carlo methods. This is something that's everywhere. I would say that this is standard, and standard for 50 years or something like that. Plenty. Plenty of time. And also the other method is molecular dynamics. So these two are the kind of big pillars of computational physics. Maybe there are more, so we can discuss that in further depth. So now molecular dynamics, what it is exactly? You have, maybe you start with Newton's equations. You have a system of 100 balls.
You have the interaction potential.
Exactly, and then you just simulate step by step. You calculate every single bounce, every single collision, and for 100 steps, 1000 steps, and so on.
For a lot of time, and you see how the system.
Exactly, and then you calculate everything you want, the energy of the system, how it evolves towards equilibrium.
Coordination length, have a lot of things.
Exactly. So
exploit.
One very useful thing for molecular dynamics that it's actually parallelizable. So you have every single step you can compute. You have, let's say, 1,100 10 to the 8 objects. You can split into 1,000 computers, and each one
cores.
Exactly, and each one computes 10 or something, and it can go pretty fast. But there is a problem that errors kind of propagate in time. So
I never did a molecular dynamics simulation, so but for sure there are errors that
that propagate
exponentially, because usually that's the case.
Yes. So we need exponentially. Is it not linearly?
That depends, but if it's like an avalanche, it's exponential. So if it's because they collide, I think it's exponential. But as I said, I never did.
But I think conceptually this is kind of the easiest to imagine. We already know the fundamental laws. You just put them in practice with 1,000 objects interacting with each other.
Molecular dynamics is linear.
Yes. Possibly. But then we have also the other side, Monte Carlo. So Monte Carlo is kind of I don't know. People say that there is no definition for Monte Carlo methods. Maybe we can give some examples, or I'll let you guys try to figure this out, and then I'll come in to give my 2 cents. So Lorenzo, if you want to start.
So you are sending to me this boiling
this boiling potato, yeah.
I have a very politically incorrect definition of Monte Carlo. It's the best way for getting what you want without losing your mind, I can say to you. And sometimes when I was doing my PhD, and I was trying to solve something, and I was talking with my professor, and sometimes I went to his office saying, "Prof, can I use Monte Carlo?" And he started laughing to me, saying, "I think you have best solution. Try first of all to do something serious, and if you are and if you cannot do something serious, we will try with Monte Carlo." Monte Carlo method is something I'm joking, but I'm joking, but not so joking, because
I'm joking.
because Monte Carlo is a nice tool, very nice tool that in theory is something quite extremely smart.
Can you give us a very simple example of a problem that you can solve with Monte Carlo?
Integrals, for example, very complex integrals, you can use Monte Carlo method for solving them. But
And conceptually, how does that work?
Conceptually, it works that you can, you can make an integral. How can I say to you? I don't want to go too much in the theoretical detail of Monte Carlo,
Yes.
but conceptually, you have an integral equation, and you can put this integral equation equal to another integral equation, but where the integrand function is a constant. So you get directly in the left side, in the right side of your equation, a random number. So you can get an equation between an integral equal to a random number. This is the basic of Monte Carlo. Correct me if I'm wrong, but this is
sounds a bit mysterious putting
is
these words.
is something that is not. This is why I don't want to go too much in the
it's,
detail.
it's not too simple. If we can I just chip in? So a very simple problem that is usually referenced on Wikipedia, or it's the kind of the first example. Is you have a system with let's say you have dice, and you want to find out the probability of.
You are solving an integral because the probability is an integral.
Yes, no, but I mean I want to make it more simple for a broader audience. So you want to find out what is the, let's say, the expectation that you get for the sum of the two dice after you throw it 2 times. So what Monte Carlo actually does, it simulates this. You have a flat probability for the dice. You throw them. You throw the 2 dice once. You throw the 2 dice twice, and you throw them 100 million times, and then you just compute the expectation. So that's how it works on a very simple problem. Now, it doesn't work exactly the same way in all. Circumstances.
But you can use this technique in several different. For example, if you are talking about particles interacting, you can think about Monte Carlo is like, okay, you are following the trajectory of one particle. For example, you can think in a certain way, in this way. You are following a particle, and then you see that the particle is approaching another particle. So you get the dice, you throw the dice and see what's happening. Okay, if you get 6, the particle will interact. If you get if you get 2, the particle will not interact. And then, for example, you get 2 and say, okay, particle will not interact. And you see the particle going through its trajectory. Right. And then you will find another particle and say, okay, I threw the die, because you are passing close to another particle, because in quantum mechanics you don't have the concept of scattering like in classical mechanics. You have 2 waves that interacts in a certain way.
Yes. And
you are trying to understand in a probabilistic way what you will get at the end. So how your wave will be perturbed by the other wave. This is what is happening. But what I say to you, Monte Carlo, what I say to you, and this is why I said before, Monte Carlo is something not serious, but not so serious. Monte Carlo is something that comes from genius mind, like Enrico Fermi. They were genius, and they used Monte Carlo effectively in a very strict way, and in theory is something perfect. In practice, you have to deal with complex system. When you're using Monte Carlo, you need to throw the dice so many times that no computer is able to handle this computational work. And you have to apply some little, how can I say to you, bias. This bias that are standard deviation mitigation, reduction of standard deviation, they are completely, sometimes completely without any kind of rational justification. They are. I have seen a lot, really a lot of publication in very high-ranked journals where you have this standard deviation reduction, completely not rational. They are using formulas, method for reducing this standard deviation, completely not justified. And you see that they get the spectrum they were expecting. But you cannot do at the standard deviation trying to get the result close to what you're expecting. You are cheating. My goodness, you are cheating.
It's an epistemological problem.
Exactly. I have tried on myself. I have tried that on my works to use Monte Carlo in a certain context, and then using this little trick of standard deviation, getting anything, and a solution. So this is why I'm saying to you, it's something serious, but not so serious, because the use you can do of this tool sometimes is a little bit, I think, not so much correct. And this is why it's better, first of all, to have a clear idea on how the process go in theory, and also using a simplified solution coming from analytical methods or computational methods, but classical, like finite elements, finite differences.
So you need a baseline. You need something to compare it to. You cannot just use computational physics or something that you don't have any sort of theoretical framework for.
You have to have you need a clear idea of how the process is working, and forgetting
or at
this
least
idea,
some elements of the
some
process.
elements. Then you can use these elements for getting out your idea of how to reduce the standard deviation, justifying it, and then you can get a nice, interesting results. But after all this process, and sometimes you get that after you try to solve your equation using standard methods, analytical methods, semi-analytical methods, you get the solution and say, maybe Monte Carlo was not useful. I have my solution. Maybe my solution is already sufficient for what I need.
But when we are talking about computational physics, are we not necessarily, because I kind of gave this example of analytical method, semi-analytical. Like you have, some elements of the system already. You have some theoretical framework. But we are doing computational physics because we want to know more than how the system behaves, more than just these few things that we can calculate, right?
Yes, but we have to. First of all, no one is able to predict the future. First of all, sometimes there is this misleading
it's even harder to predict the past, actually.
For sure. This is even more complicated because it's a inverse problem and it's not stable and it's a dangerous and misleading technique sometimes. So unfolding technique is something very dangerous and misleading sometimes. But what I say to you is that someone has got this very dystopic idea that physics can predict the future. It's not true. You can guess the future using your theory, and then understanding that you have a problem on your input, you have uncertainty of your input, this uncertainty propagates in your system, and then you get just a guess of the future that in 100% of the case will be exactly what are you expecting. So you have simulation and the reality goes exactly in the opposite way. And after that you have to take your simulation and try to adapt the simulation to your system. It's
that depends on what
for sure.
system. If it's chaotic, it's true.
For
if it's
sure.
not chaotic, you can predict the future. Actually.
For sure, I am exaggerating it because I come from the turbulence field of study. So you know this is why I'm for example, in a linear system with linear equation, your simulation is very very close to what you will get in the future doing a simple experiment.
Yeah.
But at the end, what is important is that you have a clear idea of the theory beyond, and also a clear idea that the statistical methods are the last chance. You have to consider them as the last chance before going sometimes. If you can solve a system using analytical methods or semi-analytical methods, use them. If your system is too much complicated and you cannot do nothing, okay, it's time for statistics. But first of all, study the differential equation. Study how to solve a differential equation. Study mathematics.
This is important, and it's basically the difference between just computational and computational physics, because the word physics means something. It means that you need to have a physical understanding of the problem.
Of course.
So yeah, but it's also like Monte Carlo methods that basically are based on random number generators. Allows you to make experiment that you wouldn't be able to do in reality. So that's what also today we call in silico experiment. It's a new word in the last decades.
In silico? Sorry?
In silico.
In silico.
That means in computers. Because you use computers to do experiments. That is something new. And before, experiments were in the lab.
Yes, of course.
And this is what all computational physics brought to the field. That it's an important also
alternative to when you cannot do an experiment or you cannot
need
find out the
a
insight.
theoretical understanding on the problem. That's I agree with you. But the advantage that you can do an experiment even in cases where you wouldn't be able to do
an experiment.
Or you can even just do hundreds of experiments that in reality they would cost
billions and billions and infinity, basically. Yeah,
a great
very
amount
true.
of money, and you earn money in this case using computation.
I would like to take the conversation back to some of the points that Lorenzo made. So we talk about Monte Carlo and then prediction. You also gave the example of, we have these two particles, maybe they come close, maybe they interact, maybe they do not interact. Now, this kind of implies a succession of events, right? So we have two particles, now they're here, they interact or whatever, and then they move over. So Monte Carlo is not actually dealing with the evolution of systems.
No.
So when you do Monte Carlo, we are not talking about molecular dynamics. It's used to evolve the system from time equals 0 to time 1,000 steps in the future. It can be 1 hour, one month. Yes, it's not exactly. But with Monte Carlo, in this scenario, we apply Monte Carlo to a sub problem. We are not applying Monte Carlo to the full physics problem.
Indeed, we could say that even molecular dynamics uses Monte Carlo.
Yes, in that case. But I just wanted to make the distinction. We talk about prediction, and usually prediction is something that happens in the future somehow. But Monte Carlo actually does not deal with prediction in the future. It deals with computing. Yes, it deals with computing different parameters of a system. That's it. So you basically simulate one step if you want.
One.
But not
many steps.
Yes. Or you just reset the system 1 million
many times.
But not the evolution of the system. It's just the same system, and then you put the particles in different places.
Yes, Monte Carlo is used for reproducing an equilibrium situation.
Yes, exactly.
You have reached because at the end we are talking about thermodynamics at the end, because I don't know why, but when we are talking about physics at the end, thermodynamics arrived, and so you are starting to think about equilibrium system, and at the end Monte Carlo and all the simulation try to reproduce you a situation of equilibrium. I'm not so much expert on molecular dynamics. I've just used my Monte Carlo routines for my field, which is electron and photon transport inside media, where I was used to simulate this situation of equilibrium. So, for example, inside a detector where there was passing X-ray radiation, and so understanding how much the radiation is absorbed and how it's absorbed, but in a static situation, so without time. But at the end, Monte Carlo is saying to you just that you have an integral, and you can an integral, and you can solve the integral using this trick of the random number. So if you have an integral equation involving time, like memory in server, there is no problem, I think, to apply Monte Carlo method.
No, yeah, but you apply it at each time step.
At each time step, for sure.
You can apply Monte Carlo, but
for reproducing. So what I'm trying to say is that you can use this technique, but taking clear in your mind what effectively is it. So at the end, you are always solving an integral. This is what is Monte Carlo.
Yes, an integral of sorts, depending on the situation. One thing that I wanted to ask you also, because you mentioned the problem of equilibrium, like we use Monte Carlo whenever we reach or we are interested in the equilibrium of a system, and then we use Monte Carlo.
Time-independent problem.
Time-independent. Okay, yeah, sure. So, have you applied Monte Carlo?
Completely.
Yes. I was thinking about the Gillespie algorithm. That's why.
No, can you give us some insight into that?
Finish what you were saying.
The idea is, can we apply Monte Carlo in a situation where the system is not under equilibrium?
Out of equilibrium. Yes, I think we can. But and indeed, I was thinking about this Gillespie algorithm. But also in that case, you apply it in a static situation. Then, just explain basically how the algorithm works. It's an algorithm used to simulate chemical reactions. So you have reactants that and you in a macroscopic way. So you think of the reactants as molecules that collide each other, and then they create another product of the reaction. It can be another molecule. So you have you can write your chemical reaction, that is a kind of mean field solution of what happens. You have two atoms of hydrogen, one atom of oxygen, and it will become water. Okay. With the Gillespie algorithm, you simulate what is going on microscopically before reaching the stationary solution that it's equilibrium. Okay. So. And it's also based on Monte Carlo techniques, so that was I was thinking. But what happens is that you use, you select one of the particle and you simulate the collision, and then if you have only one reaction, it's easy. It's just so the product is only one, but you can have also several reactions. When you have chains of reactions, then you can do it with this algorithm. So, in this case, you use twice Monte Carlo, because you use it to select what reaction is going to take place, if there are several. If there is only one, of course not. And you use Monte Carlo also to simulate the time that is going to take that reaction, because you certain distribution of the times that is Poissonian in general, because there are collisions, so usually you take Poissonian distribution. And you use Monte Carlo to draw a time of the reaction, so the time when the reaction is gonna happen. You take Monte Carlo, but also in this case, I wouldn't say that Monte Carlo it's a dynamical algorithm. It's not. I agree with you that it's not, because you apply it just in two separated steps of the algorithm. So, but still, you are out of equilibrium in this case, because you didn't reach the stationary solution.
Yes, yeah.
But this is not really related to Monte Carlo, because you use Monte Carlo to select the reaction and to draw a random number, basically. So you use it, but it's not related to the fact. Monte Carlo doesn't know if the system is at equilibrium or not. In this case, it just you have a distribution, you draw a random number, then you let the system evolve. But
So in that sense,
I would say that you could use Monte Carlo in a system that is out of equilibrium. It's not at equilibrium, but it's not the core of the algorithm. It's something that you need to use.
Okay, so it's at least nice to know that Monte Carlo can be used in more ways than molecular dynamics. Let's say approach can be. So it's maybe it's fit for many purposes. Monte Carlo.
That's for sure.
In this sense.
Enrico Fermi was a genius, in fact.
But
also Neumann.
But I don't know who came up with Monte Carlo. I think I checked
during the Manhattan project.
It was Metropolis Monte Carlo. I know that this was the name, the original name of the algorithm.
Metropolis. That is also used.
Metropolis was one of the people. And then Monte Carlo, because Monte Carlo is actually the casino place. And
but it's true that Metropolis uses the fact that the system has to be at equilibrium, because you use the energy, the Hamiltonian of equilibrium of a system.
Okay.
Yeah, the Maxwell distribution.
Yes. Let's now focus a bit on to the things that a computational physics does that are not necessarily physics related. So now we are talking about our software skills, basically. Like we need to, as a computational physicist, we need to know some sampling methods, I guess, right? We need to know the time complexity of our code and so on. What else could you name? What are the other concerns that some physicist building some code should have? Like what other things that are not necessarily physics? So what do you, when you write your code, what do you consider?
When I write my code, actually I do it wrong, because I don't necessarily think to optimization of the code, that, as you said, it's still important, because you have a limited amount of resources, limited amount of memory, and limited amount of time, so it should be important. It's my bad. But
do you feel like it's standard for physicists not to?
I feel like that, because we are not trained for it. When usually you have, if you have, because not everybody has courses on computational physics.
Actually, I really want to ask you both. What is also your formal education in these topics that you use?
I did it in France. I had also small, like 3 ECTS of informatics.
ECTS,
the first year in Florence.
Only first year? First year of the bachelor's?
The bachelor.
Wow, that's very little.
It was very little, but in France it was I did more computational physics.
In the masters?
That was it wasn't only informatics as it was the bachelor. In the master I did much more. But still.
So are we talking 2 courses, 3 courses? How many ECTS?
I would say 9 ECTS.
9 ECTS. Okay.
9, 12.
So that would be just for the audience 2 full 24 lecture course that you take on over a full semester.
I never remember that.
This is the 6 ECTS.
Okay. And anyway, what I wanted to say, that they don't train us to code properly. that
Okay.
it's, maybe could be improved.
Yeah. How do they actually train you in those courses? And then
Yeah, you have the physical problem, and
so it's always a physical problem.
You
It's
start
not
from
they don't teach you
physics.
like software engineering on its own
they
and
don't
so on.
teach us that. So
Okay, same my experience.
you start to solve it from what you know about coding, but you're never taught what is the proper way of coding.
Yes, yeah.
So you code, and then if the result matches your your theoretically understand the problem, you're happy. But maybe it's gonna take for hours, and it could take much less.
Yeah, 2 minutes or less, half a second.
If you were
A good coder. Lorenzo, what about you?
I was thinking that no one can be omniscient like God for sure. So the problem is that while you're using the tool, which is this dumb machine that everyone calls computer, and you're using information technology language that could be with a compiler or without a specific compiler, so compilated language and not compilated. For sure in physics we are using compilated languages because without them it's not so easy to get a nice solution in a fast time. And you have to know a lot of things about your tool you are using. The tool you are using, so the C, for example, C language, is full of nice tricks that you should know because...
Did you get taught C or Python?
I more use it to C language and
Okay.
Fortran.
Okay, before you continue, Stefano, were
at
you
the
taught?
bachelor, I was taught C and then Python in France. Yeah.
Okay. For me, just Python, Lorenzo.
And there are lots of tricks you should know. These tricks can make the difference from 2 months of hell and 2 weeks of nice work done quite fast.
Mm-hmm.
And this is why it's not easy because, for example, if you are a physicist or an engineer, you are passing your time and your life studying theory, studying physics, studying old physics, quantum mechanics, relativity, and after that you understand that if you want to get some numbers from all this theory, you have to know this tool, and this tool has got, for understanding how to use this tool, you have to give the entire your life, and probably after the entire your life you will still miss something very important of this tool. And sometimes things are not converging, you don't understand why in your computation things are not converging, and then you understand that it's just a problem of how you built your code instead on how you understood the physics and what is the core algorithm of your code. Life is difficult, and this is why it should be very important, especially inside the academic field. But I have seen that it's not easy to get a strong collaboration with different departments and departments.
I agree. It's important to talk each other and to
So
discuss with people.
much important because I cannot know everything. I need
It's really important.
a nice guy coming nearby my desk, sitting nearby me, looking at my code and start to say to me, maybe an information technology scientist, and starting to me, you have built a shit, this code is completely a shit, and there I'm in silence saying, I'm sorry master, teach me the truth. And they start saying, you don't understand the shit of computational language, you are donkey.
That's pretty toxic,
It's always,
calling, I think.
When I talk with information scientists, information engineer, it always goes in this direction. They look at me saying, your code is a shit, you didn't understand nothing of what is information technology, you should try...
You should give up.
You should give up trying everything. And I
These
said
are
to
not
them,
good colleagues then.
and I looked at them, smiling, and say, "No, you have to review my code and start to do it quite fast because I'm in a hurry." And this happens also in my daily working life. But so we are in a hurry. So stop saying shitty things and look at my code and help me. This is very, very important. But what I'm just trying to say is that talk quite easily, and also saying you are doing bad things. I think you can do it better in this way. Optimize it. And you say, you are right, help me, and take the knowledge, the know-how.
You shouldn't be shy to ask
You should not be
for
shy.
help.
I mean, I 100% agree with the collaboration aspect of it, but as a student, I mean, who can you ask? You only have your colleagues that also don't know. So
You can ask to other students.
I have a
Yes,
nice
but,
political incorrect answer to you. If you want, I can say to you, but I
Please,
don't want to be trying to go to knock at the door of an information technology, say, please help me. I will be forever grateful to you if you help me, and I will bring to you a nice cake if you help me after my after my PhD or after my degree. But please help me. You can do all this.
Yeah, or you can ask
but
for other
it's-
students. I mean,
Yes,
it's also good to.
of course, to
share your
collaborate.
knowledge.
Yeah. No,
It's
that's
still a way
very
of
true. But
collaborating.
I think if we talk about things this way, as in you can never know anything, you should ask your colleagues. Of course, I mean, this is something you can do now. But I think as a culture in physics departments, they don't do enough to teach us the basics of good software engineering, good code practices, and so on. I was completely clueless of everything.
I agree.
When I
that,
got into industry, I was humiliated, absolutely humiliated, because everything I wrote, the computer scientists were like looking in this,
Like,
like scared.
Padre
What is
Pedro.
this? Yeah. Diavolo.
Yeah, it's true.
But can I ask to you, what do you think is the basics of information technology?
I mean, software engineering, knowing how to, if you have an application, maybe you want to compute, let's say, an integral, right? You want to. Yeah, exactly. You should have the basics. You should know some methods, nice methods to do it that are fast, that are not cumbersome. So, like we do physics. I mean, when we do physics, we are given multiple topics. We solve a problem in thermodynamics, in electricity, in da 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 da. The same with software engineering. I think it would be a good idea to split like into very basic problems. Of course, when you are taught in school, in high school, if some people are, some high schools don't teach computer science or anything. Some do. But you start like with arranging lists, I mean, that's one thing that you can do. And then maybe you have trees, and then you want to go down the tree and arrange something in the tree. This is one type of problem. But what I'm saying
that's
is,
very comfortable because I want Stefano. Do you agree with him?
what I'm thinking is,
I will roast you now, huh?
Of course, I'm waiting for it, gladly. So, as physicists that we use computing, we know what we are dealing with. But then you can abstract it. Like software engineering is basically making your problem in terms of code very abstract, and then like putting it into building blocks and trying to formalize, the relationships between your code so that it flows nicely. So then if you need to solve an integral, you have a variable for maybe the result of the integral. Like you have to have a workflow for each sort of problem. So in my opinion, some software engineering course, yeah. No,
Do
go
you
for
agree
it,
with
go for it.
him?
That we should study software engineering.
No. I asked to him what is the basic of information technology.
What is the
And
basic?
the basics that we need to know as physicists, or the basic as
The basics you should need as a physicist.
Of information technology.
So I mean, first of all, object-oriented programming.
Yeah,
Okay, everybody needs to
Mhm.
know this. And then I think also we should get taught how to build like a more complex project. For example, in software engineering, it could be like build a website or something, because you need to know. Actually, the way that I learned software engineering is looking at a more complex project, like building a website, and then learning some of the ropes. Like you need to have separate files for different,
How to organize.
yeah, how to organize the folder, and after you learn this basic workflow, it saves up so much of your time. You need to know how to comment on code. You need to know how to, whenever you like build a new function or build a new object, you need to comment it properly. You need to define your variables very nicely. Then the functions inside every object needs to be defined, like named properly, each and every one of them. So there's very many, like very little steps that for somebody it's like why are they there? But they're there.
Coding practice.
Yes, exactly. Yeah. So I think literally this is one of the solutions, because this saved me a lot, and Lorenzo, please. Kill me now.
No, I will not. You are one of my best friends. So you are my darling best friend. Stefano, do you agree with this point of view?
What do you want me to say? That the basic of information technology is entropy, and I don't know.
You're starting from Claude Shannon.
In my opinion, what are you saying to me is not fixed on the basics. You are saying to me you have a problem and you have to solve it, and you have to understand how several blocks works together for getting your solution quite fast, because you explain it to me like with the same. I was like you when I was doing my thesis, when I was in the master degree, and then not in the PhD, but especially when I was a student at the master degree. And I was looking at the information technology just like an instrument, and I was really annoyed to have to deal with all these difficulties. And I was saying, okay, but I need to go to the solution. I just wanted to solve this shitty problem in the fast, and taking the blocks and putting them together for getting my solution. This is not the basics of information technology.
No, this is what it means. What is training? So.
No, I think, but the projects that you are working on, I assume you need to get to the solution. Okay, I agree. But
yes,
it would always be like a month's work or 2 months work to get to that solution, isn't it?
This is why I'm saying to you that this is the approach common in the students, that after 5 years of studying theory, they should get they have to get a solution of theoretical problem using computational physics and information technologies, and they are saying, okay, I have to get the solution, but I don't know the tools, so I need someone that explains to me, but there is no time, so and they are not dealing with the basics.
Yes, I mean that's
the
why.
Basics.
What are the basics?
Yeah.
The basics, in my opinion, are divided into categories. First of all, the knowledge of the operating system of your computer. This is something that no one explains to you, but knowing and studying how your PC works and your operational system is fundamental. This is the first one. The second one is the basics of your language. You say to me that you are dealing with object oriented, so Java and Python, C#. And Python is something a little bit particular. I use Python also in my daily working routine, because Python is something extremely dangerous, but also extremely useful, because you have packets for everything. If you have to solve something, there is the packet for doing this. So you put just 2 sentences inside your code, use the packets, put the parameters, and get your solution. Mm-hmm. This is something extremely dangerous, because you don't know what is inside the packet. And
it's a black box.
It's a black box.
Yeah,
it's extremely dangerous.
They should understand what you're doing.
The basics are the basics of information technology. The use of definitions of variables. If conditional sentences like if, else, while, for. This is the basic.
basically.
If you
and the
understand
basic-
this, you have the core of what is information technology. So how to
But it's the core, it's not the full basics.
yes, and it's true. In fact, this is the core of how your machine, how the high level language of your machine is working, because you know just the high level, you don't see the assembly.
Yes.
And this is fundamental. After that, when you have to get the solution fast, you get Python, you get your routines, you put them together with a few lines of code and try to get your best. But when you have to understand why things goes wrong, without these basics, you cannot understand. This is why it's a pity that information technology is not taught very well, because it's something auxiliary. It seems like auxiliary. No, it should be in the life spot of every scientist. And but not how to use Python, the basics. The basics. What is the assembly? What is the basic instruction? How to use the basic how to use only the basic instruction for getting solution of complex problems. This is something that imagine to solve your problems just using the basics of information technology.
I mean, that's what we basically do as physicists. We just get taught for, if, and how to define variables, and then it's like,
You get an
go for
enormous
it.
code.
Go for it, you know?
Do whatever you want.
Yeah, exactly, yeah. Just,
It's up to you.
but I
After
think
that,
this-
you give up and say, okay, I take Python and I try to use a
I
package.
think that I agree with you, but it's also true that we miss some training in optimization and organization of the code. We don't know.
good code practices. Like I think this expression kind of encapsulates everything.
I think.
But also,
Error, like we need to define
And
errors
also
very
how
well.
it works, the operating system, we are never taught.
This
about
is
it,
absolutely
so-
opaque to me, for example, even now.
I don't know either.
but also how to manage your files, your directory. This is something basic that
So this
can
is
be,
part of the basics.
But when you are doing modification to your software, everyone knows that at a certain point you do modification that say, okay, maybe I'm missing something. Where I did put the modification? I
That's
started
why
to
you need
modify
to use Git.
use Git.
So Git is also a basic.
But we are not taught.
Yeah, we are not taught how to use Git. So-
I'm learning now.
Yes,
I mean, I'm always checking like the basic functions with you know, Git upload or whatever. I
Git
also
push,
forgot them now.
Git
Git
pull.
push, Git push, yes.
Commit.
Git extract, Git whatever. Commit, yeah.
Sometimes it's tricky, how it works.
Yes. But I mean,
Still, I have to get into it.
yeah. But when I got taught this, like the soft computational physics, there was nothing like that. Like you say, you have a physics problem which is very simple. Maybe it's a lens, and you want to find out where is the focus point or whatever, like the point where the lines converge, you know, or something like that. And you basically simulate rays from every point, and then you say, okay, it's here at 2.5 meters away or something, whatever. So I mean, and you can solve this in basically in infinite ways. You can name your variable however you want, and
You're not taught.
So
About,
I think this is absolutely critical, and it's something that you know
Could be done better.
like you said, it could be 2 weeks of very nice work and very relaxed. You know where to go to do everything, or it can be 2 months of hell. And the problem is, those 2 months of hell will definitely prolong to 6 months, because you will need to come back to the code that you have written badly.
Yeah, but
sometimes.
I'm
So-
talking to you with pain. This is just explain to you the pain of a lot of years of my life. So it's.
I mean, it's
I'm
likewise. I had
getting
the
out
same. I had the same experience in industry while I was working as a junior data scientist. Is because I wasn't taught these basic things. I was very lucky to have a very good mentor that taught me everything I know, basically. And you know, little by little, I started learning the basics, and even now I'm lacking a lot. But you know, when I'm now starting a project, you know, first of all, I'm taking, even though it might take longer in the short term, you know, I'm first of all thinking of how do I define my files. When I'm starting to define objects, I'm defining them nicely. I'm commenting them properly. I'm defining errors whenever I need to. and so on. And in the end, whenever you have to troubleshoot or do some debugging, life is so much easier.
Yeah.
So I think that's just one of the rants maybe that I wanted to give, because it's a common. I mean, it's common amongst us, and it's common amongst the industry. I mean, amongst the community. I think.
Physics.
Some people, like I have a very good friend, he was into computer science since he was young. He didn't have a problem, like he was always vectorizing and doing all this. Like he was talking to me, we were 18 and we were doing some Python, he was talking about vectorizing and what are you talking about, man? Like I don't even know. And I also did high school I did computer science. But are you aware of the computational resources available to you? Or during your PhD and now during your postdoc, Stefano? Were you available of, can you use, do you have like a cluster that you can use or anything like that?
Actually, it has always been a pain to understand what are the sources available for me here in Bologna, especially in France. It was clear because it was sort of organized. Here it's more a mess because there's no an informatician who manage all the system clusters that we have. So it's less organized, but more or less I know what I'm allowed to use in terms of
would you be given money to
GPU or CPU?
To, for example, use Google Colab or something like that if you needed to?
I used it sometimes, and this was a pain. Sometimes it breaks your your threads because you're out of time. You have to start again.
So usually you rely on the thing that is given to you by the department.
But now, usually I rely on the physics department. We have some clusters. We have enough memory at least.
For smaller
Nothing
jobs.
works perfectly, but sometimes the server shuts down.
Is it what operating system is the?
That's Linux. No, it's Linux. Linux
It
server, but I
crashes?
don't know. Sometimes it crashes.
Whoa! Okay.
Or maybe someone restarted it
Okay.
without telling us. It's possible as
He's
well.
the cleaner, he
Yeah,
just wants
that's,
to clean that really nicely.
Too many processes. Let's keep.
he just goes to clean the dust and then kind of pushes the button. Lorenzo,
Yes,
for you,
more or less.
resources.
No.
Did you need any extra, or your computer was enough?
When I was in the PhD or
yes,
now?
Yes, PhD. We are
And the
talking about
PhD, it wasn't. I have experimented a better situation than the one is saying Stefano. It was quite easy to understand where there was the server, how to use them, and how they were managed. But I think it depends a lot by the different groups. They in my groups they were all this kind of nerd, very fixed with the information technology, and they were extremely jealous of their servers, so no one can touch it or get entered without permission. It was not so. It was. I can say to you, it was good managed. But it was just the only one positive point I can remember on that experience.
The only one. But it was clear for you what you could use. Where
Yes, it was quite
to me,
clear.
like even the IP address of the server, it was
No, for me,
it's a mystery.
for me it was quite easy. It was. I was liking, at least on this point. I am grateful. For sure, I'm grateful to one of my professor that I had in my PhD, because I learned really a lot of things from him, and this was related to the part of quantum mechanics. I really understood a lot, especially on the details of calculus, doing calculus with the quantum mechanics, doing simulation with quantum mechanics, solving with numerical methods the Dirac equation, and also doing the calculation of the quantum numbers, and also the Clebsch-Gordon coefficient, and all rules, doing it by hands, and it was extremely useful for understanding what is rotation theory. I'm extremely grateful to him, and also because he gave to me a lot of advices, not only in physics but also in life.
On to another more physics-related question. During your PhDs, would it have been possible for any one person in your department to still do his physics job without the use of computers?
I would say no.
It can be
No,
as
there
long as
is.
that answer.
But if you do experiments, maybe. If you do experiments, you can still. But usually in the instruments that you use for experiments, there is a computer as well. So no, I would say no.
Lorenzo, for you?
I agree with Stefano. Maybe all professor can have this advantage to not use computer, but today you need information technology. No.
If you do really pure theory, yes. Maybe somebody in the lab, I can think to a professor that was doing computations by hand. But
You need
very rare.
LaTeX for writing your equation.
At least.
I mean, if we take that out, if
You need LaTeX.
At least writing an email, that's necessary nowadays. That's sure.
Yeah, of course. But when you talk about the fundamental physics inside, is it still reachable without, let's say, any one person in your department while you are doing the PhD? Could they have reached the same conclusions without?
Yeah, those saying some pure theorists. Yeah.
Okay, so we are only talking about theories.
Some of them, yes, but it's very rare.
Some of them that have a slave that put their mind and their theory on the LaTeX. Then they can. If you have a slave that can use LaTeX and put your theory on LaTeX, is okay. You can do it.
Interesting answer. I'll leave it at that. Now on to more historical or philosophical topics. So historically, the first attitude of the physics community was to doubt whether computers could actually aid in physics understanding. What would you say to those physicists with the knowledge that you have today? They would just say, we have theory, we have our semi-analytical methods. We can do an experiment and find out if our theory works. Why do we need these computers?
If they want to get a little bit of money from a company for getting their activity going through the future and continuing their activity, they will need it, because without information technology, I think they will be not able to convince no one that to give them money for continuing, I think this way, because if you don't have at least a little bit of information technology to put a nice PPT, PowerPoint about your work, this is also information technology. I know very, very little information technology, but a little bit. And then if you want to sell your research, you have to get numbers from your research. You will need information technology for computing numbers.
I mean, you could have a calculation ruler. Or you could have a slave that does the computation for you on paper.
And we'll use the computer.
Yes, okay, so of course. So it's even presentation-wise, I mean, everything is made easier by the use of computers, basically. But now when we talk about physics, okay, I understand we can present the physics to a larger audience a lot easier. And
my dear friend, we are not the men on the Acropolis of Athens talking with Plato and Aristotle and talking about logics and hyperuranium. We are here with a very limited skills catalog respect to old man's, because you take an old man in nature and you put him in front of a tiger, and he has to solve a very difficult problem because he has got a tiger, he has to escape and to survive. This is a very complex problem, not easy, and he has to be a genius because the tiger is much more powerful than the man, much faster, and also is very hungry. Okay. And the man has to run very fast, but also has to use his brain for escaping the tiger, because his brain is better than the ones of the tiger. And the capacity of problem solving of an old man, of a prehistoric man, or a man in the past before information technology and all these shitty things coming from our future, was highly beyond the ones we have, because we are growing in a society extremely, from a certain point of view, simplified, and your problems are extremely easier than the ones of a prehistoric man. So your skills are getting in every generation. I talk about humankind. Every generation you have your skills a little bit, how can I say to you, dumped from your environment. And you have this, the totem of our society, the computer, which is a tool that thinks in the nearby future will think also for you. So it will be even more. Today is physics, science, man is strictly connected to a computer and to information technology. In the future, there will be not dividable. I don't know how to say in English.
They will be merged.
You cannot divide them. Man and computer will be merged together completely, also in a physical point of view. Possibly. So information technology is very anachronistic to talk about education and knowledge without talking about computer. It's anachronistic. You cannot do it. It's like talking about Priest in the Middle Age without the pen, and the books and writing books. Monks writing books. It was the same. Monks are related to books like now we are related to computer.
Interesting analogy. I must admit.
Yes, but you said before that you need to understand the physics behind what you're doing. So still you need some thinking. Not related to the computer.
Yes, but this is why I'm talking to you about monks, because a lot of monks in the Middle Age do not understood what they were copying, and they were copying like machine. So you can do like a monk copying like a machine a book, and for example, don't understanding that you have a page when there is written the demonstration of the Pythagoras theorem, and you need paper, so you erase the Pythagoras theorem for writing on this paper, Bible or another historic book, like what happened. Recently they found this paper of the Middle Age, and using X-ray they found the Pythagoras theorem demonstration that was erased for getting the paper. And you can do it this way, or you can understood what are you copying, because at the end you are copying in a certain way, adapting the past and what is in literature to your case, and getting something that is a little bit new.
I would like to ask you two questions before we finish. One, both of them are a bit philosophical. So the first one would be, do computers make a fundamental or revolutionary difference in the way that we see physics and think about it? Also, given infinite resources to simulate anything quickly, would it allow us to discover new theories?
I have to answer to this.
You can make it one.
No.
So fundamentally, is
you cannot. You will not have the resources.
If you have a black box that is absolutely infinite and you can put anything in it, can you?
All people are talking about quantum computers, saying, "Oh, one day we will have please stop this. Also physics. The human brain is something complex, but is nothing not perfect. There are several other papers talking about the how can I say to you, the errors inside the human way of thinking things, and this is the same of a computer, which is a machine that tries to emulate a brain, a human brain at the end. And also with this development of quantum computers, there for sure that we will have new computational power. A lot of problems we will solve it in a faster way that we have. They showed that with the quantum computer will be extremely easily.
No, but fundamentally, does the computer change the way that we think about physics? As in, before, you start with a theory, you just start with pen and paper, and then you think about abstract spaces and maybe symmetries and so on. But now, is the computer adding anything new? Like right now, we are thinking about symmetries, but we are also thinking about somehow. Maybe simulation. It's always on the physicist's mind.
Computer help you to understand better physics and to understand better what is happening. But at the end, there is your brain. And I can say to you, for sure, it's not useful to think about computer. Computer is entangled to the man, in my opinion, but it's not an infinite resource, and you have to think of what you have. Nice but already primitive representation of your brain.
Stefano, do you have anything to add?
No, I think it's already happening, because in the physicist's mind, you think about simulations. If you discover a new theory, you immediately think, how can I simulate it? How can convince other scientists that my theory is right? And very often is
with a computer.
So it's a new kind of experiment that we have now. So I think there's a fundamental difference from the past.
And also, it's the case that you said before. You can run 1 million experiments in reality if you wanted to do them.
Exactly.
Then you would need
allows you to have much more power.
Flexibility.
You can change the parameters.
So it definitely changed the game, as in computational physics
It did.
Really pushed the progress of physics in the last, since the computers appeared on the scene.
I would say that it improved a lot.
Can you name any discovery that wouldn't have been possible without the use of computers? Both of you.
I don't know. I'm not so aligned with new discoveries, so I don't know if there is a discovery that's without, if I understood correctly your question, that a discovery made from a computer.
No, as in, we have, for example, the accelerated expansion of the universe. From the period of Hubble, we already knew that the universe is expanding, but accelerated expansion, I think you still need like a satellite in space and needs to gather data and so on.
It's something. It's the extremized way that there was that nice man trying to understand the radius of a black hole, doing nice calculation of a theory of Einstein. I don't remember not Chandrasekhar. The radius of Schwarzschild. He was doing computation of the most simplified case of Einstein relativity with one. I don't remember the detail of the. Now we have the same things doing in an extremized way. I think we are doing almost the same that were doing the old physicists, but in an accelerated way, because this tool is just making us to accelerate the time for getting question and try to get also answers.
Of course. is there, and this is the last question, is there the same impetus for physicists to study the evolution of numerical methods as it is to study the evolution of physical theories? So
I don't understand you. So
yes.
Is it?
So we definitely the common sense thing to say after all this conversation is that computational physics is really one of the staple of our education, and it's something that we need to do physics, right?
Mm-hmm.
But the way that we are concerned about, at least the way that we receive our education is we start, with Newton, and then we go into thermodynamics and, evolution of time, then we go to GR, then we go to QFT, statistical mechanics, and so on. So, we
it's a
going through,
historical.
it's a historical progression of our physical understanding. But we need we are doing a lot of hours per week of computational physics if we are doing a PhD in physics or so on. And there is so much history related to computational physics. Like we have numerical methods, we have sampling methods, we have all these different, Monte Carlo and molecular dynamics, and we have a computational physics journal, and we have, a lot of resources that so my question is, should there be like a push to understand more deeply the history of numerical methods? Would this help in our physics? Because it's pretty much, you do it every day now. We do it every day now. So.
We do it every day.
But it seems like we are almost forgetting about there is a history related to this stuff, and it's also like 70 years old now. So
it was seen as a tool, not something that changed the physicist's mind.
Okay. Yeah, no, I like that actually. I like that answer.
Your question is very nice, because I can say to you that for sure you have to invest your time for understanding the basics of the very basics of the information technology, for understanding how you can better use it for optimize your computation. But this is in parallel with what is physics, because you have to see these things as two parallel straight lines.
Mm-hmm.
You cannot just follow one. You have to follow both of two. It's anachronistic not think today that you have to follow these two straight lines. But sometimes I can see that, especially in the new generation, they don't have quite clear in mind what is also the basics of physics. So I can say to you, you have not clear idea what is the basics of physics. You don't understand nothing on the basics of so what
engineering.
In engineering. I can say to you, to several persons, I have this extremely nice way of interrogating people, asking things to people when I want to, especially when I was in academic career, and I had to examine someone or during I had this way that the student was here and I was here and doing the question without looking at his eyes. But when there was some mistakes from that part, I started to look carefully straight to me and say, this is something not completely correct. Could you please rewind and try to explain me better what are you talking about? And the students starting get a little bit uncomfortable. And then I started there with my without looking at him. And the second error, no, this is not correct. And then my looking goes directly to him, and I have looked at scared faces of this approach. And one of my best questions that I do is sometimes, why Newton is so famous? Why the Newton equation is so important, and why it's so deeply changing the physics of that time? So what makes the Newton equation something that in the previous 2000th year wasn't present? What makes the Newton equation special respect to all the theories were developed before? This is my question to all the students. What do you think about?
I mean, so would you want us to answer that before?
Yes, I'm answering to you. What makes the Newton equation so special?
I mean, first, So just the equation itself.
He wants to withdraw.
F equal to
physics
m
diploma.
for
F equals
acceleration.
F
F equals ma. What makes this equation so special respect to the previous theories?
I mean, before there was no theory similar to this. I mean, maybe Bernoulli. No, actually, Bernoulli developed.
Bernoulli?
Bernoulli. Maybe
Bernoulli.
he developed his theory a little bit. I mean, he must have. No, definitely must have. I would say it's definitely like the framework behind it. So it's what is called philosophically like a paradigm.
Trying to in the mirrors, you see.
Conceptually.
Conceptually.
I think nobody thought of 2 points and how they interact with each other.
What do you think, Stefano?
I would just say it's more general. The generality that.
So maybe generality. Yeah.
This is something that
make.
I mean, it's a general question, so you can answer it in very many ways. So you're like
for sure.
You're like how would I call it? A very strict professor that is not happy with any answer. Like this is the way that you treat.
This is something. This is a question that I use with especially with the young person starting physics because I understood this concept quite late. I didn't realize this concept, but effectively, it's one of the first equations you have in the history where a quantity is not real. Not real in terms that you cannot measure it directly. You cannot measure directly the force. This is the first time that you have something related to a dynamical system where there is something that is not directly related to a measurement. The force.
You can measure the force. Why you say that?
Indirectly, you measure acceleration. You measure the elongation of the spring. You measure the mass. You measure the acceleration. You don't measure directly the force. This is the first time you are taking into account something which is postulated, which is the force, and you can measure it just indirectly.
But I mean, also the acceleration can be. You can say
you have the accelerometers with the mass.
Yeah, but you measure the length and you divide by the time at the end. So.
Yeah, you still have. Yeah.
What do you call a direct measurement? Because it's tricky, yeah. Because
it's tricky. I know.
Now they define all the measurement system. It's based on Planck constant.
It's tricky, but velocity is something that you can experiment every day. You accelerate. You are increasing your velocity.
Force, you punch someone and say, yeah.
But this is also
strong force.
But you are experimenting your energy. The force, you understand, because you know physics, you know that the force is the way that my energy goes to another body, and you are the vector effect is a vector that you transmit the energy from a body to another, but effectively it's something postulated.
I think it's a question of semantics, to be honest.
I don't know. Yeah, maybe you're right.
No, it's something. But what is extremely interesting from my point of view is that you are actually using something that you use the term force for getting the idea, but at the end, if you try, and this is what happened with Hamilton, to rebuild your theory in terms of energy, you have a completely set of theory new theory that is converging with the other one, getting the same results. But in terms of energy. So maybe, and there wasn't also the same problem because you were postulating the concept of energy, because you can measure the temperature by looking at the increase of the highness of the mercury inside the little tube, but I don't know if I can get, also because in English it's not easy to explain this, but because after that you have the continuous theory, and you have Cauchy postulating that inside the body there are stresses. No one measured them inside. You have just indirect measurement. This is something directly connected to the concept of force. because we have the equilibrium, and Newton is making the same concept of equilibrium. So you, for having equilibrium, you have all the forces balanced. This is something deeply postulated, in my view.
Forces, yeah. So now, reaching back to
But
the fundamental
this was a
understanding.
joke. This when I was talking about the students, I put them this thing as a joke. It's not something that I say to them, okay, go another time because today your exam is not passed. Is a joke, but it's a joke that makes to you, wait, I have an equation that I know like my pockets, but wait, I can think about this equation also in another
Wait.
in another way, in another light, talking about, yes, but here I have a quantity which is something completely new, postulated, not directly measurable. And this is why I'm saying to you the basics. You can learn the basics, but at the end of your life you will be, even in the end of your life, talking about basics and what means basics. And this is the same for information technology. Basics are not sounds, are basics, and you think about them every time, and you understood that you can understood better them every day of your life.
Yeah, and we never stop learning.
Yeah, of course. Sometimes, the later steps of our education actually put a light onto the more basic things. I mean, but you still have to depart. You cannot just concentrate on the basics to get understanding. So
Yes, we at the end you have to get your work and get the numbers. So
yes, of course.
life is terrible.
So to wrap this up, thank you very much for joining the podcast. Awesome conversation. I hope we can do another one some other time on a relevant topic to physics, of course. And thank you very much for listening. I will catch you on the next one. Bye.
Bye.
Goodbye.
See you next time.
Maybe you can illuminate me. I don't know what to think of it.
Can try.
Artificial intelligence and physics theories. Can a computer figure out empirically physics laws?
And now there is something new also recently came out. It is called physics informed neural networks. That is still an algorithm, machine learning and neural networks, but when you basically put a constraint that is a law of physics. Like you can put a constraint that your system has to verify Navier-Stokes equation.
Okay.
First matching between AI and physics, but I think that in the future, in principle, yes, because if a brain can discover physics theory, even a fake brain will be able to do it, I think.
So basically, if we just, let's say we feed to a system some constraints, like
and that's more or less how.
Then and you feed the system, or maybe okay. Let's put it in these terms. If you climate is a pretty also I mean chaotic systems and many other questions we could have asked in this episode. But for example, climate, we have so many sensors right now. We have them in space, we have them on Earth, in the seas, we have them on top of buildings, in the cities, and so on and so on.
A lot of information.
Exactly. If we had enough power and we just have these sensors for temperature, for wind direction, for speed, for pressure, for whatever else we have at different heights and so on of the atmosphere, do you think would it be possible, like philosophically, would it be possible for a computer to figure
the laws behind?
Yeah, to figure the laws behind?
I think that it can be possible. Now, not yet, probably. Even because we still don't know how the brain works. We still have many open questions about how our brain works, why there are only 10% of neurons that are spiking and the other 90% is completely silent, but They need to be there apparently, because otherwise they wouldn't be there. So
Right.
should be a reason. This we didn't understand this.
Yeah, that's also a philosophical kind of paradigm that in which you work in, there needs to be a reason. I mean, not necessarily.
There needs to be a reason, otherwise natural
Selection. I mean, yeah. If you put natural selection first,
because
then,
they are a cost for our body. Because
they consume energy, the same amount of energy.
even if they don't spike. Of course, a spike in neuron consumes much more energy.
Yeah,
but,
yeah.
Even a neuron that doesn't spike is still a cell. That is a living cell. It consumes energy.
Right,
So,
right.
But there is for sure a reason that we don't know yet.
It's a safe assumption.
And but once we will understand how the brain works, I think that.
But would you because now I mean we already know Navier-Stokes equation.
Yeah.
But would it be possible, for example, for that computer, once you feed it all the data that's coming from the atmosphere, all these sensors, to discover like a new way?
A new Navier-Stokes equation.
Yeah, a new,
would
for
work
example,
better.
Yeah, some new shorter one. Or
Yeah, I think it can be possible. Then you still have, also computers can be wrong. So
of course.
that's why. Okay, you have Monte Carlo simulations. You have all the computational numerical algorithms. But still, sometimes you don't know if it's the theory, if it doesn't match with the theory. Sometimes you don't know if it's the theory that is wrong or the computation that is wrong, because if you don't have a full understanding of the problem, sometimes you cannot be sure what is wrong. Maybe it's the computation that is wrong, because
yeah, there's also this problem with neural networks that you can over-specify your problem. You introduce
you
too
do
many
overfitting a lot.
So
And also it depends on what you teach to your neural network. That it's even true for our brains, because if you teach like the physics from the 15th century to our brains, maybe we would think in another way.
True.
We would our physics would be different. So, but I think that there are still maybe some steps to work out, but one day will be possible.
Have you ever felt as though you should not concern yourself with programming and only deal with deep physics understanding?
As Lorenzo was saying before, the kind of question that he was asking to his students, I think sometimes you need to do it, and it's good to ask this kind of questions, because it doesn't have to be you push the button and you wait. You have to think. Even thinking of what is new with this theory, what this theory changed in the way physics is understood. It's an important question. You need this.
But do you see programming as a second order activity or something like that?
No, it's important, but it has to go on the same side. Let's say it has to go.
But in practice, how does it go though?
In practice, sometimes you don't ask questions. That's the
you
problem,
just
because you just trust what the machine is doing sometimes, but in this way you miss something. For me, you miss something, and in this way it's just computations. It's not computational physics, because the physics still should be there. So you need to think. You need to think in a smart way also to do the computations using physics, because
and
you can do brute force simulations and just put them and wait. But sometimes, many times actually, there are also smarter ways to do simulations if you use what you know about physics.
Did you encounter any shortcuts from theory or some semi-analytical approach that I shouldn't have done all this 1 month work using Monte Carlo or whatever,
happened,
and then
yes. It happened. Now I don't remember exactly what was the topic. What happens also sometimes that you realize that you don't need to. There is a symmetry in your system, for example. You realize that at the end you don't need to do all the simulations for all the space, for example, because
right,
the symmetry. You just do half, and you have also the other half automatically. And this is something that if you don't think before what you're doing,
you do twice the calculations.
Just wait, or you wait twice the time, basically. So you waste time. This is the tricky part of having a lot of power, a lot of computational resources. Because you can think just, okay, I trust the computer, I don't think, but it shouldn't be like this. And I think Lorenzo would agree as well.
Yes.
And that's why you have to ask yourself questions.
So is the job of your supervisor, because I mean, supervisor in my experience, they don't usually deal with your code, for example, right? They will not work on your code. Is the supervisor kind of that conscious for you, as in asking you those questions or making you think of those questions?
That's why it's good to ask students also this kind of question that are different, and maybe a student wouldn't expect this kind of question from who is examining you, is evaluating you.
And does this happen?
The way the student answer, it's not. I mean, like in the question before, there wasn't a right answer.
Yes,
there wasn't.
Yes.
But just the way to ask yourself that question and think of it, it opens your mind sometimes, and you need to do it.
Yes.
When you do research, you definitely need to do it, and it can be the work of your supervisor, but at some point it has to come from yourself if you want to do research, because at some point you don't have anybody that says you should ask this question.
Yes, of course. I don't remember who told me this, but yes, I actually do remember. The supervisor of a friend was telling him that, basically PhD students there are some problems that you need young brains for. Like the person to do the hard job of actually computing and, sitting in front of the computer and so on. Sometimes even, this deep understanding that we talk about, the symmetry and so on, it's nice to think of it, of course, but sometimes it might be maybe a simpler task to think of symmetry and to think of, what are my constraints, and rather than, doing the actual computation. So in this dynamic, at least the supervisor acts as a conscience, but when you're working on your own, or you don't have, that sort of close collaboration with somebody that's higher in the rank and with more experience, then you need to do it yourself.
At some point you need to do it by yourself.
But still, the hard work is still sitting in front of the computer computing, and
the hard work is computing, but you need both.
And what do you think of your daily practice, the daily things that you do? What is the thing that takes most of your time?
I think this also depends on what is your point in your career, because as far as you go, if you advance in your career, the less you touch the code, the less you do practical things, and the more you ask yourself this kind of questions. So the more you have a global idea of the domain, of the field, of the project, or what different people are doing on the same global subject. And you need to ask the work at this point. At some point of the career, the work is really asking yourself the good questions. Learn how to ask the good questions, because there are also bad questions. This is the most difficult part of a research. The most difficult job of a research.
Finding the correct questions.
Find the correct question. Before that, you need to have some experience and you do also.
Yeah, of course. The manual
It's,
labor.
at my point of the career, I would say that I spend most of my time coding.
Coding.
At some point, yes.
Mhm.
Also a little reading papers and asking questions from a higher level point of view. But now still most of my time is coding.
Thank you
So-
very much, Stefano. That was it for now.